In this video, we have two capacitors wired in parallel along with a power source. Our power source is 12 volts. Our capacitors are 2.5 microfarads and 7.0 microfarads. And just a quick comment on how I know this is parallel wiring. There's a couple ways to look at it. So if I highlight these two nodes real quick, I can say that when current hits that upper node, it has a choice. So it can either go through C1 or through C2, and that's how I know that they're in parallel. But that's not really precise enough sometimes if we get into more complex networks. The way I need to define parallel wiring more precisely is not just that there's a choice between branches in the circuit, it's that I'm absolutely guaranteed that the voltage is the same across each of the items that I'm calling parallel. I'll say it this way, it's guaranteed that delta V is the same. And the reason why, if I look at the picture, is that the high side of each of these capacitors is directly connected with wire. The low side is directly connected with wire. So the high and low sides always have the same potential. So the potential difference must be the same across those two elements. So if I look at question A, it says compute the energy stored in each capacitor. And the reason this is possible without even doing any simplifying of the circuit is because I know that this top node is at 12 volts, is directly connected to the positive terminal of the battery. This bottom node is at 0 volts. So each capacitor has a potential difference of 12 volts over it, and I should be able to use my capacitor energy formula. And I'll just post a link real quick to the video where this was derived. It's 1/2 CV squared. So I end up with 1/2 2.5 microfarads, 12 volts, all squared. And I get 180 microjoules out of this. And I think those units are fine for this problem, so I'm not going to change it into scientific notation and use joules. Let's find the energy stored in C2. That's 1/2 times 7.0 microfarads times 12 volts squared. And I get 504 microjoules for that. Okay, now let's get the equivalent capacitance for this circuit. So my typical notation for this is to use a big arrow and then indicate what I'm using at each step as I simplify a circuit. In this case, I use the formula for the equivalent capacitance of two parallel capacitors. And that's simple, you just add them. And there's my equivalent capacitor. You might want to write down the calculations separately down here and say CEQ is C1 plus C2, which is 2.5 microfarads plus 7.0 microfarads, giving you 9.5 microfarads. Now, what are we doing with this equivalent capacitor? In this case, I just wanted to illustrate that our energy calculations come out the same when we use this equivalent capacitor. So I want to find the energy stored in it. I can see that there's 12 volts across it. If I draw these two nodes, the high side is 12 volts, the low side is 0 volts. So V is equal to 12 across this guy. And I get E capacitor equivalent is 1/2 times that equivalent capacitance times the potential difference across it squared. And I get 684 microjoules. In the question, we're asked to verify that it adds up to the sum of the two energies in part A. So I'll just use a little more compact notation here. E1 plus E2 is 180 microjoules plus 504 microjoules, and that is indeed 684 microjoules, so it works. If you find the physics content on Zach's Lab helpful, click on the Zach's Lab logo on the right to browse playlists and subscribe to the channel. I produce over 100 new videos per month, and subscribing is the easiest way to find new content. Thanks for watching.